Uh, Jan told me to remind everyone that we need to leave our badges in the box out there before we leave. We're very pleased to have Jeehoon Park from Seoul National University. He's going to tell us about an algorithm, flat F-manifolds for Labial smooth projective complete intersections.
Thank you for the introduction. I'm greatly honored, really honored to speak here. And thanks for the invitation. It's wonderful, Kim's workshop. I'd like to say some words about Minhyuk, even though he doesn't like it. My first encounter with Professor Minhyuk Kim is 2000. That was my last year of undergraduate study. And my actual correspondence with him is 2001, when he was in Korean Institute for Advanced Study, and he organized a name called a special semester in arithmetic geometry. It's kind of 6-month program, 2001. And he invited a series of, many of famous leading mathematicians in arithmetic geometry and number theory to Korea in 2001. And then there was a very spectacular event. I mean, not just for me, to many people in Korea at the time. The number of lectures, as far as I remember, like more than 1,000 lectures during the 6 months. And then there were like all lecture series, not just one lecture. Like at least 4 lectures, 90-minute 4 lectures, and one of them is like 12 90-minute lectures, but lecture went on, and sometimes it's 2 hours. It was an excellent event. And then to name a few mathematicians which were invited, and you might be surprised. There was John Tate was there, and Kazuya Kato was there, and Jean-Marc Fontaine, and Pierre Comès, and Henri Damon was there, and Christopher Deringer was there, and Michael Rappaport was there, and Christopher Soule was there, and Ralph Greenberg, and Spencer Bloch, and the big names. And I thought that is very cost effective. I mean, those are not Fields medalists, but they're like research levels is up to Fields medalists. And he chose such a person at the mathematicians at the time. And then I tried to attend like lectures, but of course I was just a student, and that was very difficult. It's far beyond my knowledge. But fortunately, Minhyuk organized pre-sessions, and then for students. So at the time, I had so many stupid and naive questions to him. But whatever I asked, I mean, his answer was very insightful and yet down to earth. And that was actually a mathematical cultural shock to me. And I nurtured, myself. I mean, dream of becoming a mathematician. I mean, through those experiences. And not just me, I think his existence made a huge impact on my generation of number theorists in Korea. So using this opportunity, I like to thank him with my D part. 선생님 감사합니다. 생신 축하드립니다. Okay, that was.
There was negative impact.
I'm the example of negative effect. You will see. And this talk, I mean, it's a bit far from, the maybe theme of this workshop, maybe not much. Anyways, I'd like to tell you I sort of, dealing with this kind of stuff, because I started my career as a number theorist, and after that, special semester events, I went abroad to the United States, and I got my degree under the supervision of Glenn Stevens at Boston University around 2007. So I studied p-adic modular forms, p-adic theta correspondence, and p-adic L functions, and Iwasawa theory, that kind of stuff. That was my main object of study. Okay, so I liked it, but there was one problem. Problem was that the subjects was kind of too hard. There were many black boxes for me, I mean, in that business. So, for example, here's my flow, how to get this kind of stuff. So there's a p-adic theta correspondence is about p-adic variation of theta correspondences, classical ones. So I had to understand the theta correspondence, the classical theta correspondence. But in order to understand theta correspondence, you have to know the existence of wave representation of metaplectic groups. So I heard that the existence of wave representation in metaplectic groups is related to the Sturm-von-Neumann theorem in quantum mechanics, and which tells us that the formalism of Heisenberg picture and Schrödinger picture in quantum mechanics are equivalent. And that's what usually mathematicians stop, right? And you got that, existence of wave representation. You can prove it using representation theory, blah, you stop. But for some reason, to me, because I was a colleague around me, close friends, working physicists. So for that reason, I went further because I could ask questions, that my colleague. So I studied more about quantum mechanics and more generally quantum field theory. And that subject is broad and it's very hard. So I had a very hard time to digest or study that subject. But in the meanwhile, while I was struggling, I think it's 2015, like it's September, around September. Min Young Kim suggested me to collaborate, with him on his brand new subject, arithmetic gauge theory. So 2015, with a group of some of Korean mathematicians. Here's some examples here, Do Young and Hwa Jung. And so this brand new subject, arithmetic gauge theory, in particular, arithmetic Chern-Simons theory, which he adapted the language of language of topological quantum field theory to the theory of Galois representations and their L functions, and based on arithmetic topology, which studies the analogy between knots, links in three manifolds and prime ideas in spectrum of algebraic integers, things like that. So I was kind of very happy with that, offer suggestion. I'm honored to work with him, and that made me another reason to study quantum field theory, because it's about topological quantum field theory and like Galois representation and number theory. So at the beginning of this arithmetic research on arithmetic Chern-Simons theory, I thought that I could use Chern-Simons theory, arithmetic Chern-Simons theory, to understand quantum field theory. But that was somehow wrong. It's the wrong direction. Number theory and geometry is too far. So studying this, my shallow knowledge on Galois representation doesn't help to understand this quantum field theory. So arithmetic gauge theory is not mathematical physics. I like the terminology. It's physical mathematics, right? So there's a famous quote by Eugene Wigner, the unreasonable effectiveness of mathematics in the natural sciences. But if you dualize that, that's unreasonable effectiveness of physics in mathematical sciences. That's the motto of physical mathematics. And that was a sort of physical mathematics. So it's not sort of a right, object to study, quantum field theory using that. So I was looking for a sort of another sort of more closer subject to physics, and that is this kind of stuff. Which is meter symmetry and Frobenius manifolds, and there are pioneers in meter symmetry in this room, Professor Candelas and Lausa. And then this topic is the sort of some sort of minor topic in the structures appearing in the meter symmetry conjectures and Calabi-Yau manifold. This is my title here. Okay, that was my long excuse. It's already 10 minutes have passed. So let me start the formal talk. So it's my main object of study is this smooth projective component. So this is a common thing. So I'll start from homogeneous coordinate ring. For the projective space, Pn. And for simplicity, I will work over just C. It could work with the field of characteristic 0. Then I'll think of smooth, projective, complete intersection, right? Pn defined by polynomials in C, and whose degree is C. That's my XF. So for simplicity, let's just say the complex analytic space, complex manifold associated to this smooth projective component section variety, X. Okay, so it's I'm thinking of projective embedding, too, and it's a smooth, so it's complete intersection. So this one is dimension n minus k. This is dimension n. So that's the meaning of complete intersection. And as the title says, I mean, I missed the CY in the version I sent to the organizers. I also assume X is Calabi-Yau, so canonical bundle is trivial. So in this case, in this particular model, that is equivalent to the degree restriction. Add all the degree, then that's the number of variables of this projective ring. So I'll assume this. Okay, so that's the basic setup. Okay. Now, let me briefly recall the notion of flat F-manifold. This definition is due to Manin and Hertling. This is kind of weaker, slightly weaker structure than Frobenius manifolds. I mean, Frobenius manifolds is kind of that axioms of Frobenius manifolds was introduced by Dubrovin in his study of geometry of two-dimensional quantum field theory. And later, people extracted the crucial properties of the Frobenius manifolds and weakened a little bit, and that's this notation. So here's the data. M is a complex manifold. And Tm is a holomorphic tangent sheaf or tangent bundle. We'll use them interchangeably. And then there's a dot. This is the one tensor, which is associative and commutative. With identity vector field. So I can call A. And this M and this 2-1 tensor and the identity with respect to this algebra structure. And nabla is a connection. Then M identity vector field is called structure. Then, if it satisfies following, compatibility. So that compatibility can be written in this way. First, this identity is the flat with respect to this connection. Second, there's you take the Lie derivative of this 2-1 tensor, and that satisfies the following compatibility. So this is like 2-1 tensor, and then you take the lead derivative, it's still 2-1 tensor. So this notations make sense, and then it should satisfy this condition. And 3, right, 3 here. For every U in C, you consider linear pencil of connections. Defined that way. Is origin free and flat for every X. So this quadruple satisfies these 3 conditions, then it's called flat F-manifold. So if M has a metric, say Riemannian manifold, like G, and then there is a Levi-Civita connection, then you can define Frobenius manifolds. So the Frobenius manifolds is this 5 thing, and such that this is a flat F manifold, and then the multiplication in G satisfies the invariance problem, like Z and like this. And then G is metric. And WIM is a structure shield, of course. So, in that sense, this is the weakening of the usual Frobenius manifold. And of course, Frobenius manifolds is like family of Frobenius algebras. And Frobenius algebras are, commutative associative algebra with the inner product, satisfying in various conditions. So it's kind of, right notion, it's good notion, without mentioning the Dubrovin's like work on the 2-dimensional like UFT. I mean, the history says that before Dubrovin, Kyoji Saito in the singularity theory, the hypersurface singularity with isolated hypersurface singularity, and then he used the theory of primitive forms and constructed the Frobenius manifold structures on the universal unfolding space. That was it, like before the Dubrovin's sort of formulation. So the Kyoji Saito didn't name it, but it turns out to be that's the actual first example. So Dubrovin's result is 96, but the Kyoji Saito is like early 80s.
Very for Frobenius manifold. When you have this G, this is C infinity real then? The G is still holomorphic, or was it supposed to be?
I think it's a
Must be real or something.
yeah. This is a real thing.
So then everything becomes C infinity.
It's a metric in the usual sense.
Yeah, yeah. Metric is a real. Yeah.
You can set up the same way for real.
Okay, now how can I study this sort of stuff? And as I said,
Sorry, just a question. I apologize for having forgotten my differential geometry notation, but Lie sub x of y is also just the bracket of x and y. Is that right?
oh, yeah, when Lie sub x and y is bracket, and Lie sub x of f is x, and then you extend it by using Leibniz rule. So all is flat F manifold structure on the primitive homology. I say this, I'm actually looking at the drum homology. But I'll omit the drum. And that's my goal. That's what title means. I like to construct the flat F manifold. So this M will be just affine space whose dimension is this dimension of the homology space. And there's primitive means, I mean, it doesn't from the homology of projective space. And it turns out that this is really the middle dimensional homology. Same as the middle dimension. That's the goal. So how can I study that? So the model I'm using is so-called Calabi-Yau.
Just a quick question. The manifold here, M, is going to just be this vector space.
Yeah, vector space. So what I'm actually saying is flat F-manifold. So it's really just a structure of formal neighborhood of around zero. It's about the algorithm. So LG here is a Landau number. What it means? So consider following space XCY. Is here. Zero. That zero is that one, and P1 to PK as coordinates on here. And I use the degree minus degree of the polynomial. So that's the sort of so-called CY model for X. And there is a reason why it's called like this. So if you look at that, there's a projection map. Then of course, this is a PN. And then if you look at the fiber, you see this is a vector bundle of rank K. Okay. Over the project. Okay. So in particular, because of the Calabi-Yau assumption, I made it here. This itself is a Calabi-Yau, non-compact Calabi-Yau. It's a smooth, non-compact Calabi-Yau. In the sense that it has a nowhere vanishing holomorphic volume top form, volume. So, and moreover, I'll consider this kind of potential F. This is a variable like this. I say, E1, F1, that plus PK. And that's the definition of F. Then, because of this group action right here, you can see this F is a well-defined function of XCY. I see. It's invariant under that C-star action. Moreover, if you look at the critical locus of F, critical locus, then you can easily compute. This is actually the smooth projective complement set. This is inside in N, and then I use the zero section. So this says, this is kind of perfect model, like zero-dimensional QFT model for the smooth projective complete intersection variety. Here the space-time is zero-dimensional. Is a space-time is a point. So there is no time and there's no space. There's no time. The one-dimensional, QFT is the quantum mechanics, right? And this is zero dimensional frequency point. And spatial fields. Spatial fields is basically sections on a bundle over this point. So in this case, I'll use the C n plus C minus 0. Okay. And there is a abelian gauge group, C star. And then there's an action functional. That's the W. So it's a function. WF. So, which is invariant on this gauge action. So it's gauge invariant. And then if you look at the Euler-Lagrange equation, the equation of motion space. That is, I already computed that over there. Example. Okay. So this equation of motion space is the our interest, right? So it's okay to call that is like CY model, like it's a CY Calabi-Yau continuous section variety. It's very simple, right? But in fact, like this simple description helps to understand in a united way that the work theory of zeta functions and period integrals of Calabi-Yau varieties. So I think this potential gets one of the first person who considered this potential is Dwork. But Dwork's work on rationality on zeta functions is 1950s, right? So it's very old. But this CY and LG model thing is after that. So it might be Dwork was the first, but nowadays it's so popular. I mean, the mathematical physicists always use LG-CY model in various places. And then he used the exponential sums of this F, and then to count the number of rational points of algebraic variable finite field. But you can also use this F to study period integrals of Calabi-Yau varieties. And then you can have a sort of similar like integral has this shape, e to the certain observables and F and certain cycles over here. Okay, so it's a kind of continuous version of exponential sums, and then they have a close connection. So this naive looking zero-dimensional field theory has some applications. Now, to slightly more at the Haley trick. So physicists call that's a Calabi-Yau Landau-Ginzburg sort of correspondence. But mathematicians has another name for this. It's called Cayley trick. This trick is about you transform the study of complete intersection variety to a study of hypersurface. So complete intersections is difficult because the equations are many, but hypersurface is only one equation and it's easy to consider. So that's the one equation related to this K number of equations. So for this, let me consider the projectification. So that's a vector bundle, so I'll just projectify. In other words, let's say P that projected. See. Relevant morphs. Zeta, eta, So if you define that, of course, the fiber that the affine fiber that becomes a projective fiber because of this action. So this will following structure. Those fibers in this one. And then, in fact, this P is the toric variety, which is associated to the apolytope. Is a smooth projective variety, toric variety. You'll cut rank 2. Whose Hooke's ring, toric homogeneous coordinate ring. Ring is given by C, X, and P. So to spare the space, I just call this Q is this variable there. So let's say this N is the M plus K plus 1. Then the Q1 is the Z0, and Q1 is Q2 is Z1, and blah blah blah. Qn is the P. That's the sort of simplified notation for this. And of course, this is a toric variety, and the toric homogeneous coordinate ring is graded by the Picard group. By Picard group here, it's just square. So it's natural to introduce the grading. Let me just explicit about this grading. So you can easily compute that the grading. Let's call charge and weight. This is xi has charge 1, and charge of pi is the minus of the degree of the polynomial, and weight of xi is 0, and weight of 0. And so that's the this grading over there. So how does it help us? So you have a P, and there's a P to the N, right? And then here I have an X. Here, you can actually check that this F is the global section of P of OP of 1, because it's a projective, so it's actually embedded in some big space. So you pull back it, and then you can actually check that everything there. So you can think about the zero locus of this section. So, and then because of the description of F, it maps down to X under the projection map. Then, if you look at the complement locus, then you can see that this one has an affine fiber. This one has a projective fiber. So that means that the homotopy type of P minus XF is equal to Pn minus X. Any degree homology, Gram homology is isomorphic to that's for NM. But the most important degree for us is the middle dimensional. So this one has degree dimension n die k minus 1, right? This space. That is isomorphic. to H n plus k minus 1 n minus x. Now, you know, there's a Giessen sequence for this Pm minus x. And inside the Giessen sequence, there's a residue map. And it turns out that this residue map is an isomorphism to the primitive part of the homology, middle dimensional homology. So it's degree 2k minus 1 here, x itself. So this is an isomorphism. So that says that if you want to understand this homology group, then you have to understand the hypersurface coupling. So that's the Cayley trig. And this one is relatively easy to understand. It's basically the twisted differential. The twisted like Durham. You have to compute this kind of, homology twisted Durham differential. In fact, this is the very famous theorem. It's a fundamental result in quasi theory of this complete intersection variety. It's Griffiths. This is k equals 1 case, the so-called hypersurface case. And later Dimka, and in general. Also, there are some names on it, like Baturev and Cox, and several people. Which name that this is isomorphic to the Jacobian ring. So CQ, I had to put 0 here, coming from the Sista square action. So this 0 means charge 0 part. 0 component. I defined that one, right? And so this is subring. I mean, there is a description when X is not a Calabi-Yau, still we have such kind of description. But in that case, this won't be a subalgebra of a C bracket Q, but in Calabi-Yau case, it becomes a subalgebra. How do you do? And there's a F, where the F is the Jacobian variety. Jacobian, not variety, because I heard so many Jacobian varieties and Jacobian ideal. So it's generated by partial derivatives. That the critical locus over there. Okay, so in order to achieve my goal, it's actually, I have to work with this stuff. So I have to put flat F-manifold structure on this quotient of Jacobian ideal. And of course, this is a finite dimensional space. And this is one proof why this is a finite dimensional and this is finite dimensional space. And then there's a computer algebra based on Grosvenor basis, and you can actually compute those things pretty well. All right, now let me move on. I have to do one more trick. So we translate complete intersection to hypersurface. Now the tree is I think it's, let me say it's a Baranikov-Kontsevich twist. When you have a Calabi-Yau manifold, even compact or non-compact, there's a lower vanishing holomorphic volume form, and then you can use the contraction with that form. You can translate the differential forms to polyvector fields, and then that changes the algebra structures. And then that changed algebra structure can be used to construct flat F-manifolds. So it's here, say the BV algebra. Let's see. There is my equation. So ACN, this is the space of smooth sections, smooth holomorphic I, anti-holomorphic J forms. on C to the N. I is the cotangent bundle. J is anti-homomorphic. That's the AIJN. And then I say AK, AR, CN is simply this grading. And I can think about polyvector space. Zero forms with values in I put so this is smooth section of tangent bundle. Anti-holomorphic coefficient. That's the by notation, and then I'll define the degree here. EV R of Cn. This is J minus I R A I J expression. And then, Cn is a non-compact Calabi-Yau, so there is a holomorphic volume form. So up to unique opt constant. So in this case, you can just think of, this one. Now, what is good about it?
Here's a trivial point, but that's not unique up to constant without further conditions. I mean, on Cn is an affine variety, so you would multiply by a non-zero.
Non-zero functions. Yeah. I mean, you're right. Yeah. But I say yeah, true. The compact case is a unique opt constant, but in this case, there's a more option. Okay. So I'll use this contraction with this omega and we have a polyvector field to interact with this form omega c. Yeah. Then this is an isomorphism. So we have following picture. And here you have holomorphic and anti-holomorphic differential. And also we have wedge field here is a sequence. Then there's a contraction isomorphism with this holomorphic volume form. And that is, if you look at this degree convention, you have e to the minus n, c to the n. right? Then now you can transform these operators to here under the contraction. Then you will see that you will have this one, and d bar wouldn't be changed, not changed, and df will change into the bracket f, and this bracket f is the Schouten Riesenhui bracket. Yeah, I always have a problem with the pronouncing. I mean, this Schouten. Riesen bracket. Up to side. So. You have a corresponding diagram, fully vector field part. So what's good about this is that after this twist, this one has a wedge product, just Pauli vector field with the anti-homomorphic differential forms, and have E bar. Now, this becomes a differential again, and then we also have this bracket, and we also have this one right there. This. So E omega C same as T omega E omega. That's the defining equation. In fact, the Schouten Riesenhui bracket can be written in this way. That this pair, and also I consider this pair. And for push 1 and 2, this is a BV algebra, differential Gerstenhaber Bartholin algebra, and this is a shifted differential graded Lie algebra. That's the point. So by the shifting, what you get is the differential graded Lie algebra. I think that's the point. I mean, without like this shifting, it's hard to cook up the differential graded Lie algebra. But in this business, with this shifting, you can get a differential graded Lie algebra. So this is a differential cochain complex, and this is the plays role of Lie bracket, and then they satisfy the Leibniz rule. Then you can actually check that. And then this, sometimes it depends on it's right here, because this measures the failure of Leibniz rule of partial omega, and this differential graded Lie algebra actually comes from this differential graded differential Gerstenhaber Bartholin-Vilkupisky algebra. Basically saying that this is a commutative associative algebra with the differential, and then there's an order 2 differential operators called Laplacian, and then these two structures, are not doesn't satisfy Leibniz rule, so you somehow measure the failure, that becomes a Lie bracket. And then this kind of packet is called differential gradient, differential Gerstenhaber PV algebra. All right, once you get it, then there is a sort of thing that you can generally apply the theory of deformation functor associated to DGLA. I mean, due to the concept.
I understand you're saying that the polyvector fields have two different structures. One is a sort of differential DV algebra and the other one is a DG Lie algebra.
Yeah.
And they satisfy some compatibility.
I mean, these two things.
Yeah.
I mean, these two just follows from one. Yeah. So what I'm saying is that there are two different algebra structures on this complex. One comes from the wedge product of differential forms, the usual one.
Yeah.
That extends to like quantum cohomology, and then it makes a quantum product. Also makes a Frobenius manifold, so-called A-model Frobenius manifold. But if you twist it, then you have polyvector field, and there is another structure, algebra structures. That algebra structure controls the period integrals, like deformation of period integrals, like Picard-Fuchs equations. And that is called B-model, sort of Frobenius manifold structures. But this one, both of them are B-model Frobenius, B-model. Not sure whether this is a good idea. See, this is so something like this. I'm actually running out of time. So general theory says you can think about the Moore-Cartan functor associated to the DGLA. That is given that way. This is the category of graded Martinian C algebra, Z graded. Okay. Then this is a category of sets. And then the functor goes like you have a Artinian algebra, and you look at the solution, say gamma, and it's P 0 P Cn and tensor with this A, and then look at the 0. So you have another graded stuff, and that's the this is the usual Moore-Cartan equation. Like you have a DGLA, and then you model by the gauge equivalence coming from the algebra. So the equivalence says that gamma prime is equivalent if gamma prime can be written as gamma bar lambda some lambda and conservative A -1. So these are actually 3-1 bracket. So, and that's the notion of the equivalence. And then you can study that one, but if the DGLA comes from PV algebra, then it's known that this functor is representable, pro-representable by just affine algebra. So in fact, it's very easy question. You see, I mean, because of the degree reason, you can actually, without restriction, you can solve this somehow. And because D-bar thing, so you have to worry about it. So really, I have to skip, I mean, some parts of the things in my head, because I have only 5 minutes. So let me just say final result. So instead of looking at this, I can work with the simplified version. Say, meaning that P Pauli vector field, PV0 Cn, this contains, right, this polynomial ring. And then the cohomology, middle dimensional cohomology was, primitive middle dimensional cohomology was, as this description. So I can somehow, make a replacement of this complex by a smaller one. It's basically quasi-isomorphic. So let's say PV algebraic 0 Cn. And then I have to think about that the charge 0 part. So I can extend the charge 0 thing too. So I can redefine a smaller complex, the algebraic polyvector fields of degree holomorphic one. So I put the 0 in the second component. And Cn, and look at the charge 0 part. So that's my definition of something new, P dot. And then there's F. And you can use this. That's the new sort of a more algebraic version of DZLA. And then I'll use that to find an algorithm. So I have to find a Moore-Cartan solution of this Moore-Cartan equation, which has a special property. That special property is basically a Picard-Fuchs equation with a little more restrictions. It can be written that way. Theorem. If there exists algorithm. Zero T. Here's a T is the coordinates. I is an index set. Whose cardinality is the primitive homology? And so you look at that, and one tensor, A, which depends on gamma. Such that here, this is the gamma alpha. So we sometimes use the notation. It's double derivative. So this sort of analysis of these Moore-Cartan equation associated to the DDLA leads me to leads me to this partial differential equation. And my goal was actually solving this one algorithmically, complete solution. And actually, hold this theory to here, it took only like a year. I mean, it's basically reinterpretation of the things in the literature. And I thought that this is an kind of easy question. But I spent actually many years to get this algorithm. Spent so many times, and finally I got the algorithm. So if you have a basis polynomials for the primitive cohomology, then I can feed into this algorithm. I can make a unique A alpha beta gamma given basis. To be precise about it. Anyway, that's the sort of main theorem. And second, once you have this structure constant gamma A, then you simply define that way. Define it, the vector field on that cohomology space. And then just define this is 0. So it's a flat coordinate with respect to this coordinate. And then this M and this, and identity with respect to identity on the equivalence relation, because here there is an identity. So identity really plays a sense there, goes there. And then nabla is a formal Frobenius F-manifold. That structure around 0. Once you have that, then this actually implies equation star implies that this is the flat F-manifold forces. That's how I get the things in the title. Thank you so much.